Good afternoon, everyone. Thank you for joining with me today to talk about design patterns for real-time streaming data analytics. So before we begin, just a brief intro. My name is Sheetal Dolas. I'm a principal architect working at Hortonworks. And most of my professional career, I have spent working with customers and solving their business problems in the field. Specifically, last more than 5 years, I've been working in big data technologies like Hadoop and its ecosystem, as well as things like Storm, Kafka, Elasticsearch, and so on. Recently, I co-developed a Cisco open source product, which is open source product for threat management and network data analysis, where we were processing 1.2 million network packets per second in real time. So over the next few minutes, I'm going to be talking about different streaming architecture patterns. We'll just take a quick overview of that. And then we'll jump into the main topic, that's design patterns. So we'll talk about what are the design patterns, why do we need design patterns, and also take illustrations of some of the design patterns for real-time streaming analysis applications. If time permits, at the end, we'll have questions and answers. But just in case there is not sufficient time, I'll be hanging around after the call, after the talk. So please feel free to come back, ask your questions, and discuss any concerns that you might have. I'll be happy to talk about it. So with that, let's get started. So as you can see that businesses are seeing a big value by processing large amount of data sets on platforms like Hadoop. And now customers are asking that, I need to process large data sets in real time. Batch is not sufficient for me. So to address that need, Apache Spark and Apache Storm have been instrumental platforms to do real-time analytics. However, if you want to build applications on top of them and make them really scalable, make them sure that they're working well in all different conditions, as well as meeting your latency requirements and meeting your throughput, is not an easy task. So having done this multiple times in field, we saw certain patterns keep repeating again and again in every application. So we try to distill those patterns in design patterns, and that can be made applicable for majority of use cases and can be reused. So before we begin, let's talk about different architectures in streaming. So we'll see this architecture or some kind of variety of this architecture in almost every streaming application, where you have source applications. So there are source systems which are generating data. They might be syslogs, machine data, variety of data. The data is then captured by data collection tools like Flume or any other custom tools that you might have. Once you collect the data is typically sent to a messaging system, like Apache Kafka being one of the most popular messaging systems in real-time applications and scalable applications. And from there, you feed that data into the real-time processing engine like Storm. Where the data gets processed, you have multiple topologies running there. They process data based on your business need, business logic. And once the data is processed, the data gets stored into storage layers, where you can have one or more storage layers based on your needs. You can have storage layers like Hive and HDFS, where you can store all the historic data and do analytics on historic data sets. Or you can store the data also in search engines like Elasticsearch or Solr, where you can do real-time text search on your data sets. In addition to that, you may also want to store data into NoSQL engines like HBase, where you can get very low latency access to the data sets. And finally, you have access layer, where you have analytical tools like R, Python, BI, etc., which are working on these data sets. Or you have web services which are using this data and providing the final results to your consumers and giving them the outcome of this analysis. Also, you might have alerting systems which are fed by your real-time analytical systems based on certain conditions, and those alerts might get fired through various mechanisms. So you'll see a variety of applications follow similar architectural pattern. In fact, this is the architectural pattern that we use for Cisco OpenSOC. There is another slight variation to this called Lambda architecture, where essentially what it says that you have new data that comes as a data stream. That data gets fed into the speed layer. Speed layer is essentially nothing but something like Storm or Spark, where you process your data and you generate your real-time views. Very similar to previous architecture that we have seen. And then these views are accessed by your data access layer through various query mechanisms. So that addresses one part of your application, that addresses your newly coming data and real-time data. At the same time, to get the better insights with data and do better, deeper analytics, you feed this data into batch layer, where you have all the data, your master data and all the historic data, which you can analyze and pre-compute your views based on historic data sets, which may not be possible in real-time systems, because you may not have enough data sets available in real-time streams. And then you again put those pre-computed views into serving layers, where you have batch views. And finally, these batch views are again queried by your data access layer. Now, your data access layer can query your real-time views as well as batch views and get best of both worlds. That's the Lambda architecture. There is another parallel to this Lambda architecture called Kappa architecture, which essentially says that there is nothing called batch. Everything is stream. So all your data comes as a stream, gets fed into the stream processing system, where you have multiple jobs and multiple versions of each job. So some versions process only recent data, some other versions of job process all the historic data. And then they generate the output views. They get accessed. So you'll see one or more of these kind of architectures people might be using, and they might fit their individual needs. Now, having talked about these architectural patterns, let's get into the design patterns. No matter what architectural pattern you use, there are certain design patterns that are going to be applicable always in stream applications. So let's first talk about what is a design pattern. So design pattern is a reusable solution to a commonly occurring problem in given context of the software design. So this is very important. It's in the given context of the software design. Design pattern is not a design of a specific use case that you can just take and implement. Neither is it a code that you can just take and start running it. It's more or less of a template of how to solve a problem, or best practice around how to solve certain problems that keep coming again and again in the field. So why do we need design patterns? We have been seeing design patterns for years and years now. Java has so many design patterns, JEE has so many design patterns. Why do we need more design patterns? So if you look at this, streaming applications have really different characteristics. Unlike batch applications or unlike traditional applications, they have different characteristics. It is a continuous data stream, which means that it's unpredictable. You don't know what kind of data you are going to get when. Your streaming applications are expected to run for hours and days and weeks and months, so it's hard to predict what's coming, what is going to come. In many cases, you might want to join data from two different streams. And data might come from two different systems. They might have different impedance. They might have different frequencies. They might have their own latencies. Unlike batch applications, when you are joining data sets, in batch applications, you know that this is a snapshot of data on which I'm going to do join operations. In stream, it's not like that. Data is continuously flowing. So it's hard to do joins. On top of that, you may have situations like you might have out-of-sequence events that come late. So these streaming applications have really different characteristics. Definitely, you can use some of your old design patterns in streaming applications as well, but there also is need for handling these new patterns and addressing these new needs. On top of that, if you have high-scale continuous data speed coming in your stream applications, that poses different challenges. You're going to have peaks and valleys, right? On certain particular days, on Thanksgiving and Christmas days, you're going to have peaks coming in. On Valentine's days, you might have peaks coming. And these peaks can keep changing over a period of time. The data sets that you get on Thanksgiving and Christmas are going to be very different than data sets you get on Valentine's days. On Christmas, data set might be skewed on certain things. It might be skewed on geography. On Thanksgiving, it might be skewed on something else, maybe, again, geography. On Valentine's days, it might be skewed on user age groups. So the data characteristics keep changing. The external world events determine what kind of data you're going to get in your applications. So it's hard to predict what's coming. And with that, if you have to maintain your SLA and latency and maintain your throughput, it's really a hard problem. So we have seen this in Cisco OpenSOC, where we had to process 1.2 million network packets per second in real time continuously. It was a hard problem to solve. And that's where we need design patterns that can help us solve these problems by reusing what we have learned in the field. So there are multiple design patterns, right? You have architectural patterns, real-time streaming architectural pattern that we talked about, the first pattern that we talked about. There is a near real-time streaming pattern, which essentially is a micro-batching extension of the first architectural pattern that we have seen. There is Lambda architecture we talked about, there is cup architecture we talked about. There are functional patterns like stream joins, or finding top-end records, trending topics like Twitter. Or you have rolling windows, you want to perform operations on certain rolling windows and get outcome of that result. You have data management patterns, like you want to do external lookups to enrich your data sets. Or you want to shuffle your data more responsively so that you can adapt to your changing pattern of the data sets. Or handling out-of-sequence events. On the other hand, you have security patterns like message encryption or authentication and authorization. So today I'm going to focus on data management patterns because these are the patterns that we have seen come repetitively in field and not talked about a lot, not documented a lot. Other patterns, you'll see a lot of documentation here and there, some sample code. These are the patterns which are continuously coming but not yet talked enough. And that's why I'm going to choose some of these patterns to talk about in today's talk. If you want to talk about other patterns, feel free to catch me after the talk and we can talk more. So let's look at external data lookup. So what is external data lookup? So external data lookup is basically referencing frequently changing data, which is managed by external system, and using that data for either enrichments or filtering your data sets, or even for doing validations. And you want to do this by maintaining your SLAs of throughput and latencies. Now, what is the problem? Why is it difficult? Why do we need to have design pattern for this? And there are certain challenges around these data sets. That the moment you start referencing data from external systems, you are going to make calls to external systems, you are going to increase your latency of processing. And if you are processing thousands of events per second, or hundreds of thousands of events per second, that's going to just keep adding up. Then you might decide, okay, why not I cache my entire data set into my memory? Let me cache it in all my bolts. But the reference data might be huge enough that you can't hold in the memory. Or even if you can hold in memory for now, your data characteristics can keep changing, your transaction volumes can keep going up, and you may end up having issues on scalability and performance issues later on. In many cases, even if you cache, the reference data is changing. So you need to refresh your caches, purge your cache, rebuild your cache, and you might spend a lot of effort in just managing your cache and not processing the real data events. On the other hand, if you're making continuous calls to the external systems, your external systems might not be as scalable as systems like Storm, and they can become bottleneck. Either they can crash, or they can limit what is the throughput that you're going to get into your systems. So what options you have? So you have multiple options how to address this, right? One option is you always go and fetch data from external system. It comes with its own challenges. Or you can say, I want to cache everything. That's going to come with its own challenges. Or you have third option that you partition and cache on the go. And that's the option that I'm going to talk about, which we have seen that work best in most of the cases. So what we mean by this particular option, and to illustrate this option, let's take a reference use case. The reference use case, it's a real-time use case and real-life use case, which I have simplified a lot just for this talk purpose. And I have taken all the complexities out. The use case is like this. You have credit card transaction data coming from some source. Typically, it would come through Kafka or something like that. And you have external system where you are holding information about users' last known location. And that might be captured based on your mobile devices and GPS devices and whatnot. And that is managed in external systems. What we want to do is, as the credit card transaction comes, we want to see where this transaction occurred and what is the last location of the user, and find out the geographical distance between these 2 points. If the distance is sufficiently large, let's say 100 miles or so, it's an indication that this is a potential fraud, because user cannot be at 2 different locations, like 100 miles apart at the same point of time. So how can we address that using this design pattern? So if you are implementing it in Storm, it will look like this. You have source system, which is generating the credit card transaction data, and sending it to the spout. So in Storm, when it comes, you send that data to a partitioner bolt. Now this partitioner bolt is going to partition your data based on certain criteria. In this particular use case, we are going to partition this data based on the area code of the user's mobile numbers or phone numbers. And then that data is then sent to the fraud analyzer bolt. The fraud analyzer bolt, which is going to look at this data, reference data from external system, match, compute, and say whether it is potential fraud or not. As simple as that. Now, if you drill it down further, this is how it is going to look like in Storm. Or even if you have any other scalable system like Storm, typically this is how it will look like internally in the system. So you have partitioner bolt, which has multiple instances, which is getting data from a spout. That partition bolt looks at the instance, looks at the event, looks at the area code, and then decides which particular fraud analyzer bolt this event has to go to, and partitions based on that specific key. You can choose your own keys based on your business logic and business needs and your data. You definitely understand your data better than anybody else. So you can choose what is the key on which you want to partition your data sets. The fraud analyzer bolt, what it is going to do is, as it gets event, it's going to see, okay, I got an event for California. Do I have reference data in my cache? I don't have it. Let me go and fetch from external system, fetch it, put in the cache, do computations, and send the result. Next time I get a record for California, again the fraud analyzer bolt says, okay, do I have data in cache? Yes, I do have, so I can use it from cache. So I save a trip to the external system. So I'm caching that data. And if you're using tools like Google Guava or any other lightweight caching libraries like that, it can help you automatically manage your cache life cycles. So it will help you refresh your cache based on certain intervals or based on certain criteria. So things can become much more simpler and easier for you. Now with this strategy, you know for sure that my instance number 1 is always going to get all the California data. The California data is not going to go to instance number 2 or any other instance, which means that I have better prediction and better ability to decide what to cache and where to cache. I don't have to cache entire data set in all the instances, which means that as my data grows, as my number of instances keep growing, my cache capacity also can keep growing up. And I can scale with my data sets. I can scale with my transactions. So what benefits do we get out of this option, right? So one thing is, of course, you're caching only the data that is needed. You're not caching entire data sets. You're caching based on transactions that are coming, and you're choosing what to cache. On top of that, each bolt is caching only part of data. So eventually, you are achieving the effect of caching entire data set, but you're actually caching entire data set in fragments, which means that the requirements for your RAM are going to be reduced. You can cache more data with the less resources that you have. Now, data is, of course, locally cached, which means that number of trips that you're going to make to external system are going to be reduced, which means that your latency is going to be improved, your system bottlenecks are going to be reduced. Cache can be time sensitive, like Guava and all these things can give you time sensitive cache, which means that after certain intervals, the cache will get refreshed automatically. You don't have to do anything explicitly for that. And since it is on-the-go cache building, you don't have to worry about fault tolerance, because building cache is a primary nature of this design pattern. So what happens if a bolt dies, if a host dies, or if a JVM dies? It starts somewhere else again. It follows its own natural pattern. Data comes, do I have this data in cache? I don't, I go and fetch it and start building my cache. So you don't have to do anything explicitly to handle failures. So this just gets automatically addressed. So as we talked, the design patterns are contextual. Not every design pattern is applicable everywhere. So each design pattern has its own applicability. So where is this applicable? So of course, this is applicable where you have stream processing that depends on external data sets. And the external data set could be huge that you can't cache. Or your external data set is continuously changing. Or you might have scalability limitations on external system. You might be storing your reference data into MySQL or something else which cannot scale like Storm. So if you have one or more characteristics of this, you can use this design pattern. Moving on to next, responsive shuffling. So as you all know, in distributed systems, we keep passing data from a compute node to compute node and a component to component. In MapReduce, in Storm, we keep passing data from map to reduce and reduce to reduce, or bolt to bolt or spout to bolt. This data passing is called shuffling. So what is responsive shuffling? So responsive shuffling is automatically adjusting the shuffling for better performance and better throughput during the varying data natures like peaks and off peaks and data skews. So what are the challenges in shuffling? As we said, the streams are expected to run for hours and hours, days and weeks and months. So you are continuously getting data streams. And data characteristics can keep changing. Their nature can keep changing. Which means that it's unpredictable. You don't know what's going to come later, what's going to come next. And you might have data skews, and data skews can change over a period of time. As we talked about, the data that might be coming on Thanksgiving and Christmas might be totally different, skewed on a specific parameter versus data that is coming on Valentine's Day might be skewed on some different parameters. And you have to react and adjust to these changing data patterns and maintain the throughput and latency of your applications. Now, since the stream applications are expected to run continuously, you don't have luxury of bringing applications down, maintaining them, fixing them, changing the patterns, and putting the applications back. Because the moment you start doing that, you lose the benefit of real-time processing. You're no longer real-time. You're always working as batch processing. You're bringing applications down, fixing, putting up. So what options you have? So of course, you have option that you can do static shuffling. So you can say, I know my data better. I know how the data is going to come. I can predict my data well, and this is my shuffling strategy. As I shuffle data between different boards, this is how I'm going to shuffle. And you hope for the best. Say, okay, things are working fine today. You hope that things will work better for tomorrow. They may or they may not. Or you can go for the responsive shuffling pattern, where the responsive shuffling itself will try to adapt to the changing nature of the data. And let's talk about what this pattern is. Again, to talk about the pattern, let's take a reference use case where we want to do optimized edge-based inserts. So the use case is that we have data being processed in Storm, and after processing, we want to process that data into HBase. Now, to get better efficiency, what we want to do is we want to group data in such a way that each HBase bolt that I have in Storm is going to send data to one or maybe max 2 region servers. So that way, I can reduce the fragmentations, and I can insert more data with less number of trips to the region servers. But as you know, the nature of HBase, as data starts growing, your regions are going to change. You're going to have region splits. You're going to have more and more regions. Or you might decide to merge some regions. So your HBase region layout keeps changing, and you want to adapt to that changing layout of HBase and regroup appropriately so that you can keep maintaining the throughput of your system. So if you don't have responsive shuffling, in default implementation, this is how things will look like. Right? So you have application bolt, which has multiple instances, which processes events. And based on certain criteria, it starts sending data to HBase bolt. And you might have multiple instances of HBase bolt. This HBase bolt essentially collects the data and sends that data to HBase by talking to the region server. So in this example, you'll see that you're processing 300 events on the application bolt, then sending 300 events to HBase bolt, which is again processing 300 events, and finally 300 events are getting persisted. But when you talk between HBase and region servers, you are making 9 trips to the region servers, which means that you have more fragmentation, more network communication, and you are doing less in more talking. Now, what you can do is you can have responsive shuffling. So basically what you can do is you can have application bolt use a partitioner. So it uses partitioner interface, and you can have custom implementation of this interface. This custom partitioner can use the reference data. So in our example, our custom partitioner is going to be HBase region aware partitioner, which goes to HBase and gets its region metadata, and it uses its metadata to identify a given record which particular region it belongs to. Now, as the regions start changing, this partitioner can go back to the HBase, get the new metadata, and adapt to the changing region layout. So with this is how your topology execution will look like. You again have application instances, application bolt instances, but they are now augmented with region-aware partitioner. Now these region-aware partitions, as we talked about, they are going to read the HBase metadata. For every event, they get the event, and they figure out which particular region this particular event belongs to, and then send that particular event to appropriate HBase instance. As the regions start changing, this partitioner is going to go and fetch the region metadata again and change its shuffling strategy. So it's going to do that automatically on periodic intervals. So which means that you don't have to worry about how your regions are going to get expanded, split, or merged. The topology is going to adapt to itself. which means now that your number of trips that you're making from the edge-based bold to the region server are reduced. So you're just making 3 trips. You get the same effect. You are processing 300 events, but you are processing with less network communication, less fragmentation, and improved latency, improved performance. Now, you can apply this logic to anywhere else. If you have data skew, you can have partitioner that looks at your data. It keeps watching your data sets and figures out, based on the data skew, how do I want to shuffle my data? Again, I keep taking the same example that one day it might see that the data is skewed on geolocation, so it can decide some certain strategy to distribute the data sets. Next day, the same partitioner sees that this data is now skewed on the age group of user. It adapts to it and starts changing your shuffle strategy so that it can make sure that data is evenly spread across all the instances, and there are no hotspots, and there are no bottlenecks. It just keeps adapting to the changing nature of data. So what are the benefits? Of course, the topology is smarter now. It's adapting to the changing nature of data. So you need to know a few parameters on which you want to keep monitoring your data sets. You can make things as simple as just monitor on certain parameters, or you can even have complex logic in the partition bold, which can do a lot of data analytics and figure out what is my shuffling strategy at any given point of time. Since you're adjusting to changing data nature and you are making sure that data is evenly spread across all the instances available, there are no hotspots, it means that you are maintaining your SLAs and throughputs. So of course, since topology is smarter, you don't have to bring topology down more frequently for maintenance. Topology is maintaining itself. So we are bringing the self-healing nature of the platform into the self-healing nature of the application itself. That's exactly where we want to go. We want applications to be self-healing, just like the platforms that we have, Hadoop and Storm. So again, coming back to applicability, where can you use this design pattern? So of course, this design pattern is applicable in cases where you have application which is not dependent on specific shuffling logic. If it can work with changing shuffling logic, this design pattern works. If you have applications which are specifically designed for certain shuffling, then this is not the pattern for you. Or you might have data that might have varying skews. And almost every stream has data skews. And given the nature of streams, almost every data sets are going to have varying skews over a period of time. Or you might be interacting with systems which are your target systems or reference systems whose layout is changing over a period of time, and that's going to impact your performance. So you want to adapt to the changing layout of the external systems. So if you have one or more of these characteristics, this pattern can work very well for you. Again, this is one of the patterns that we used in OpenSOC, where we could actually achieve processing 1.2 million events per second by adapting to the changing nature of data sets. So the next one is out-of-sequence events. So what are out-of-sequence events? So out-of-sequence events are the events that came late. Sufficiently late that by that time, you started processing events that should have been processed after the event that came just now. So what are the challenges in handling out-of-sequence events? The first thing is it's hard to determine in streaming applications that when your data is arriving and whether the data arrived is complete or not. Very rarely you can determine realistically. The second thing is, if you get out-of-sequence events, many times to process out-of-sequence events, you need a lot of reference data. You might have to rebuild your models. You might want to refetch all the data relevant to that event, bring that in memory, recompute things, and process those events. Which means that you are now going to spend more effort and more time in processing these out-of-sequence events and not process your regular events, and eventually lose throughput and latencies. Now, of course, if you want to do real-time applications, you want to make sure that your latencies are good enough. If you are doing critical applications like fraud analysis and fraud alerts, you cannot really afford latencies there. So what can you do with out-of-sequence events? You have multiple options. The first and easiest option is you just drop the event. You don't process it. Now, this may be okay for certain use cases, but many of use cases you can't really do that. You can't afford to lose data sets. Then you can decide to wait for all the events to occur before they get processed, which means that first you need to know how to determine whether all events came in or not. You need to have logic to determine whether all my events really came in or not. And now you might have to wait for a long time to get all your events, which means you're holding on to large data sets in memory and holding on to processing them, which means you're going to increase your latencies, decrease your throughput, and eventually get into a situation where you have so much data to be processed that you can't hold anymore and you'll start crashing. Or you can choose the third option, fan it out, where you can get best of all possibilities. So what can you do as part of fan out strategy? So you have source, which is having source spout and sending data. You first send that data to the event filter bolt. Now this event filter bolt has logic and ability to understand what is out of sequence event. It could be as simple as comparing the event timestamp with the timestamp of the event and the current timestamp and say, okay, this difference is huge, it's out of sequence event. Or it could be smarter, say that, okay, it can keep track of all the events that are being processed in recent few minutes, see what is their average time, and what is the time of this particular event. If the difference is huge, it's out of sequence event. Or you can have your own complex logic to figure out what is out of sequence event for your business. Now, once you find that out, you just basically fan those events out into separate bolt. So all the in-sequence events, you start sending to typical processing bolt. So those bolts will keep processing and churning your regular data streams. Out-of-sequence events can be sent out to these special handling bolts. Now your special handling requirements are complex. If they need to do a lot of different processing, you can even fan it out into different topology. So what do you get out of this? The first thing is that you are separating the concerns from processing, from design, from maintenance. You have in-sequence event processing bolts which are working on happy path. They know exactly how to process your event in the fastest possible manner. All the complexities involved in exception handling are separated out in different bolts or different topologies. Easy to maintain your code, and you can continuously keep churning your data on typical happy paths. Now, if you are separating that event, if you are panning it out into a different topology itself, you have more opportunities. Then you can scale these topologies independently. If processing out of a sequence event needs a lot of memory to rebuild the models, you can have different memory provisions for your out of sequence event topology. So you can scale them independently. So where all can you use these out of sequence events, this particular strategy? So of course, first thing is that when it matters that your sequence impacts your processing, that's where you have to worry about out of sequence events. If the sequence doesn't matter, you don't care about it, just start processing. Or if you have out of sequence event processing that needs complex logic, which needs to rebuild the model, which needs to refetch all the data relevant to that event, and it becomes more complicated. And of course, your stream has to have relatively low volume of out of sequence events. Because if you have more out of sequence event in stream, you have some different problem to solve and not this design pattern. There is something else wrong in your system, in your pipeline, that needs to be addressed first. So to summarize, as we talked about, these streaming applications are having different characteristics. Their nature is different. They're unlike batch applications. They're expected to run continuously. They're expected to run for hours and days and weeks and months without downtime. Now, there are certain cases we tend to figure out, okay, what is my current data set, what is my historic data set, and you design applications based on that. But in streaming applications, you have to also think for future. Because unlike batch applications, you don't have opportunities for fixing things. Batch applications, typically, they wake up, process data, die. Wake up, process data, die. And there is a time window in between where you can go and fix things. It's not same thing for streaming applications. So you have to think more and think ahead for various possibilities that are going to happen in your streaming data sets and plan accordingly. Simplicity makes things much more reliable and predictable. So fan out, things like fanning out, or just divide and conquer that we talked about in the caching pattern. Just make things simpler, divide and conquer, they can give you more reliable systems and more predictable performances. You can use one or more design patterns in conjunction to solve your specific use cases. So potentially you can use the first design pattern about caching with fan out. You can use caching with responsive shuffling. You can combine multiple patterns to get your specific use case addressed. And more importantly, patterns are contextual. Not every pattern fits everywhere. So you have to look at your use case, see what are the characteristics of your use case, and which patterns can you use. So with that, we come to end of this talk. Again, thanks for joining me, and thanks for listening patiently. So we have some more time where we can get some questions, and I'll try to answer those questions. Again, if you don't have time for answering all the questions, feel free to talk to me after the talk outside in the lobby, and we can talk more. Thank you. Thank you. Okay. Yes.
I'll have a question. For the responsive shuffling, you reduced the number of round trips to 3 in your example. You've left out the trips to the meta store to figure out where the events should be shuffled, and could that single region server that's holding the information that you're using to shuffle responsively, could that be a bottleneck?
Very good question. And that particular pattern doesn't go and fetch the metastore metadata for every event. It uses the previous pattern that we talked about. It will go and fetch metadata. It cache it for a certain time. And maybe, like, say, every 5 minutes or every 10 minutes, you refresh the cache. So the number of trips that you make to the region server metadata are dramatically low. They're not going to be the same as number of events. Good point, though. All right, looks like there are no more questions. Thanks again. Thanks for attending this talk and listening patiently. Thank you.